Good afternoon, everyone. Thanks for coming out and watching my talk. So today I'm going to be talking about Windows fibers. So if you're anything like me, you probably thought fiber was some sort of dietary requirement, not an operating system concept used and abused by attackers. Then it wasn't really until I dove into the topic that I realized, oh dear, proof of concept tools, malicious samples, and C2 frameworks are making use of fibers for their own gain. But perhaps more alarmingly, there didn't seem to be any robust way to detect what they're up to. So a little bit about me. I'm a security researcher with a background in agent development. Previously, I worked as a senior security researcher for WithSecure and F-Secure in their endpoint research team. And that was kind of building novel detections to the latest attack techniques, and then also facilitating some of that research into offensive tooling. And that was both across Windows and Linux operating systems. Prior to that, I worked for UK Intelligence for roughly 5 years, doing a similar sort of thing, though that was mainly more APT-focused and specifically on Windows. And then alongside that, I developed an endpoint agent. And I also worked as an R consultant at Mandiant. So what are we going to be talking about today? Well, first, what are fibers? Then, how are they abused and their appeal to attackers? Then how do we go about reversing, understanding the core components and the internals of fibers and extracting telemetry from memory? And then how do we then facilitate that into building detection tooling that works on an enterprise scale with an example use case of a tool that I built called Weetabix. So I'm going to run you through some key terms. I'm sure you probably are already aware, but for those that aren't, we've got the heap. That's an area of memory reserved for data that's created for and used by a process. Then we have the process environment block, otherwise known as the PEB. And that's a data structure that represents information about a process in user mode. Then we have the TEB, which is the equivalent for a thread. And then we have the thread information block, otherwise known as the TIB. And this is actually the first field of the TEB, and it contains a pointer to fiber data and some stack information. So I'm going to be talking about fibers in the context of Windows, not any other operating system, because their definition differs. Specifically, builds from 1903 onwards, because Windows kind of redeveloped the way it worked. Microsoft's own definition is here on the slide, but I actually prefer to define them as stackful coroutines. And coroutines are just like functions that have stacks, except they don't return like a regular function. Instead, they're manually switched from one another by the application itself. And so they don't have to rely on the thread system scheduler. They're a user mode concept, invisible to the kernel, and they run within a thread. But crucially, only one fiber can execute per thread at any one time. So if we've got any Java devs out there, think green threads. It's kind of like the functional equivalent. And they've actually been around since Windows 95. And they were initially designed when CPUs had less cores and threads available to them. Now, they were used in things like SQL database servers, or when developers wanted to implement their own workloads in a more efficient manner. But the current recommendation is actually not to use them where possible. But people kind of still do, for instance, in browsers or audio software plugins. So I find it sometimes helpful to compare operating systems and their concepts against one another to see where they sit. So fibers are essentially just mini threads, and they're actually an optional component, not a mandatory component, unlike threads are. And they're managed by the application itself rather than the operating system and a thread system scheduler. And because they exist in user mode, when switching, there's no expensive kernel transition during that context switch. And since only one fiber can be run at any one time, it means they're implicitly synchronized, which also means we don't have any synchronization constructs such as semaphores, mutexes, waitable timers to deal with. So what makes up a fiber? Well, I've tried to graphically represent how I feel fibers are made up into 3 components. First, we have our fiber object, the gray blocks at the bottom. They contain our fiber data. That's the executable code assigned to a fiber. Then we have our fiber local storage, highlighted in red. And this is the functional equivalent to thread local storage. So it allows a fiber to store and retrieve values via an index. And then each fiber has its own slot per index. So like on the diagram, we have 3 fiber objects, and we also have 3 slots per index. And then finally, we have fiber callback functions, highlighted in yellow. And these are functions a user can point to when allocating a new fiber local storage index. And they're called whenever the fiber is deleted or the associated index is freed. Now, some basic rules about using a fiber. To first use a fiber, you need to convert your thread to a fiber. Then there's actually no main fiber. So every fiber is actually considered equal. It's very egalitarian. Any fiber is free to create or delete another fiber, but only one fiber can run per thread at any one time. So fibers are controlled by this pretty simple API. And the main reason for this simplicity is the lack of those synchronization functions and constructs. Actually, only switch to the fiber, which is highlighted in the bottom left, is actually responsible for switching the execution from one fiber to another. So here I've kind of split it up into 3 main categories. You've got your setup, teardown, and scheduling functions. You have your fiber local storage-based functions. And then you have some local inspection functions. And what you'll notice is the local inspection function is actually quite limited, and they're only relevant for the current local fiber that's executing. So how might we use fibers legitimately? Well, first, we need to convert our thread to a fiber with the convert thread to fiber call. Then we might want to create a second fiber, and we supply an argument with our fiber data to execute. Optionally, at this point, we could allocate some fiber local storage and then set a slot value. And then when we're ready, we can switch the execution to this newly created fiber with the switch to fiber function. Once we're finished, we can convert the fiber back to a thread with convert fiber to thread, or we could switch execution to another function, or we could delete the fiber itself, which calls exit thread internally. So how might an attacker use fibers? Well, there's kind of like the vanilla way, highlighted in red. So as before, we convert our thread to a fiber with convert thread to fiber. Then, say we allocate some read-write executable memory, we get our shell code, we copy it in, we create a new fiber with the create fiber function, and then we supply a pointer to this shell code in memory, and then we switch execution to it. Another consequence of that is that our shell code is executed. An alternate mechanism, and a slightly more obscure way, would be to use a malicious callback. So FLS-alloc allocates a new fiber local storage index. And at the same time, you can also define a callback function. Now, this callback function is executed whenever that index is freed or the fiber itself is deleted. Realizing this, what an attacker could do is define a malicious callback, then free that index, delete the fiber, and then the consequence of this, their callback is executed. Now, the benefit of this method is there's no forensic artifact that we can gather from the TEB or the PEB or the TIB, or perhaps anywhere else that gives us the information about what the callbacks are or the actual structure of it in memory. So why do fibers appeal to attackers? Well, first off, simplicity. You've seen how basic the API is. You've seen how easy it is to use. There's a very low barrier to entry, and fiber safety is built in. Next, they're obscure and niche. So threat hunters might be aware what fibers are, but they're unlikely to know the difference between a legitimate and suspicious-looking fiber. And also, dormant fibers themselves are just parked elsewhere in memory, so there's no real easy way to get at them. And then fundamentally, what this leads to is an immature detection posture when it comes to telemetry and signatures. So most EDRs, for instance, will collect call stacks on a certain operating system event happening. So like a remote VM read to LSAS memory. And at this point, the call stack will be collected, and it will trigger how you led up to that event in the first place. Now, what events do you use to collect fiber call stacks? And then how do you tell what is legitimate and malicious, especially when an attacker can perform most of their actions in one fiber and then switch to another fiber and execute that last action which generates the call stack. Now, the call stack that we collect would miss out all the malicious actions that have been executing that previous fiber. Moving on from this, we could actually have a look at driver-supplied callback. So a lot of EDRs have moved away from user-land hooks in order to generate the telemetry because attackers can simply nullify them and get rid of that telemetry source. So instead, to add a bit more robustness, they might use like thread creation and deletion events to kind of bring some telemetry in. But the problem is, because fibers are a user mode concept, they live and die in between those two events. Therefore, we don't actually collect any telemetry. And then on top of that, there's no remote enumeration functions in the API. There's no open source tooling, to my knowledge, and there's no specific ETW-based providers. So we need to find fibers ourselves. And before we start, I find it's really good to define some clear goals of what actually we want to do and get and extract from memory. So one, we want to remotely identify which fibers are running on which threads. Next, we want to know what makes up a fiber and where it lives when it's dormant. And then we want to be able to associate those fibers with the correct set of fiber local storage, fiber callbacks, and thread IDs. We can then build valuable telemetry, hopefully, to create detections. But unlike investigating threads, as with anything, there are a few little problems and hurdles you need to overcome. So as I said earlier, there's no remote enumeration functions. There's no open source tools. And also, the documentation is severely limited. So you might be thinking, right, let's open up a copy of Windows internals. Let's have a look. There's 100 pages on how threads work. Well, actually, that little screenshot there is all you've really got for fibers, and it's not any more helpful than looking at the MSDN documentation. And then, as mentioned, there's no open source tooling, so we need to produce something novel to achieve our goals. So a good place to start is to look for those local enumeration functions for clues. So if we start with isThreadOfFiber, it does exactly what it says on the tin. It tells you if that currently running thread is using fibers. So we open that up in IDA. Turns out it's actually just really simple. It's collecting the TEB and reading the same TEB flag field and checking to see if that third bit is set. If set, it deduces a thread is running fibers. And then we can just test this by writing our own fiber program, either setting a debug break or breaking into it ourselves, and dumping that field. And yes, we can see, look, that has been set, therefore we are running fibers. So to build on this, we want to go about looking at it from a remote enumeration perspective. So anyone that's built a memory scanner before will be kind of familiar with this. First, we take a snapshot of all the running threads. Then we open the thread and use NT-query info thread to get the TEB base address. And then we just read the offset to that same TEB flags field. So doing this narrows down which threads are running fibers from that snapshot. So the remaining two local inspection functions are actually just macros. So we can open the source for them. Pretty easy. So get fiber data returns the value of fiber data. That's our read executable code, which is stored actually in a field in the thread information block, the TIB. And then get current fiber returns the address of the current fiber object, which is actually just the address of that fiber data field. So from this, we can actually infer that the first field of a fiber object will begin with fiber data. So after that step, we can determine if a thread is currently executing a fiber and the fiber data field of the current fiber. Next, we want to have a look at identifying the remaining fields in the fiber object and how to find dormant fibers and associate them with the correct thread ID. According to MSDN, to use fibers, you must convert a thread to a fiber with convert thread to fiber. Now, this function takes an optional parameter to set the fiber data field. And here's what it looks like decompiled in IDA. So what's really going on here? Well, on line 20, we can see the TEB is being collected. Following this, the same TEB flags field is being checked. So essentially, we are performing a sanity check to see if we're currently running fibers or not. Following this, on line 26, we're allocating a new heap block, crucially of size 530 hexadecimal bytes using RTL allocate heap. Now, on line 33, the LP parameter value, representing our fiber data field, is being set as the first field on that newly allocated heap block. And this, what it does, it indicates to us that this heap block is being used to house our fiber object. Then, on 34 to 44, other fields from the TEB and the TIB are being copied over to this new fiber object. From this, we can infer that fiber objects are stored on the heap, and fiber objects contain fields copied over from the TEB. But crucially, that requested heap block allocation size is a static 5 30 hexadecimal bytes on 64-bit systems. So using a similar methodology, I investigated the remaining teardown and scheduling functions and kind of pieced together all the fields in that fiber object. I then validated my findings against my own fiber program and then tested that output with WinBag to see what I might expect to see. So an interesting point worth noting, though, is there actually isn't any thread ID field in that fiber object, and we'll come on to see why this is a bit of a problem later. So next, we want to scan the heap for any potential fiber objects. So to do this, we identify the heaps used by a process. So we can look in the PEB, and we get a list of pointers to the heaps. Then we can filter for NT-style heaps using the segment signature and the heap headers. Then we can decode heap entries because they're encoded. And we can use the encoding value to reveal the true values of the heap entry headers. But what you'll notice is that in the heap entry headers, there's no requested bytes field. So we need to calculate it ourselves using the true bytes, the number of unused bytes, and the size taken up by the heap entry header itself. Once we've done this, we can generate a list of potential fiber objects based on that requested allocation size of 530 hexadecimal bytes. Now, because the heap exists on a per process level rather than a per thread level, it means we need a way of grouping fibers together based on that thread ID. Now, that's fine for currently executing fibers because we already have a thread ID from the thread basic information when creating a thread handle, and we just read that client ID field. But not for dormant fibers. We don't have a thread ID. They're just some random region of memory on the heap. So this is where the FLS data field, highlighted in yellow in that fiber object, comes in handy. So when I was investigating this, it turned out it was just a pointer to a struct whose first member was a list entry that contained a forward and a backlink, so essentially a doubly linked list. So I began testing and discovered like each member on that doubly linked list actually pointed to another fiber object on the heap. But not only this, those fiber objects were only owned by a single thread, the thread that was used to create them in the first place. So thus I found a way to associate dormant fibers with the correct thread ID and match them with the currently executing fiber. And you'll notice there's this other entry in that doubly linked list, and this points to this undefined FLS context structure, and I'll come on to why this is important soon. So after that step, what have we got? We've got a full fiber object structure, and which fibers, both current and dormant, are associated with each thread. Next, we want to identify how many fiber local storage indexes are in use and which fiber local storage slots they belong to. So a good place to look for clues is FLS get value. What this does, you provide it with an index number, and then it retrieves the calling fiber's fiber local storage slot. So often to begin with, decompilation and disassembly, you've got to do a lot of fix-ups. It doesn't make an awful lot of sense, but I find like correctly identifying the variables used, casting these to the correct types, especially if you've got some pseudo structures, and then looking for definitions that have been passed into functions higher up in the call chains for clues obviously helps you kind of makes a bit of sense of the madness. So this screenshot actually shows my decompiled code from the C runtime equivalent of FLS get value is where the bulk of the work's done. So what happens here on line 9, it collects the FLS data field. Then following this, on line 10, it checks the index value supplied to it is not above 4079. Now, this is actually a hard-coded maximum when they introduced from 1903 builds onwards when they redid the way that fiber local storage works. And then following that, from lines 12 to 16, it applies this algorithm to fetch the address stored, of the value stored in the fiber local storage slot. When given the fiber local storage data field from that fiber object. So what this did is it gave me enough clues to go and build my own remote enumeration version that I could then point to fiber objects that I'd found on the heap. And then I could enumerate through every possible index and provide some validation on the output that I was receiving to determine the number of indexes that are in use. So after step 3, what can we locate? Well, we can locate the currently executing fibers, the dormant fibers. We can associate them with the correct thread ID. We've got the fiber local storage indexes, which slots are occupied. And the final thing we need to go and grab is that callback information. So that additional entry in the doubly linked list from earlier points to this undocumented FLS context structure of size 60 bytes. And inside this, an array of pointers, and one of which actually points to a valid heap block entry that contains the callback table. So I dumped this from memory to work out the structure. The callback table is actually dynamically defined based on its size, which is highlighted in yellow, and it's the first field, and that's the number of fiber local storage indexes that are in use. Indexes 1, 3, and 4, highlighted in green, are actually responsible for the teardown of fiber local storage. So they're like a standard set of callbacks. Anything beyond this are user-defined ones, such as those which I demonstrated earlier from the FLS alloc function. So discovering basically how this was structured and how it works allowed me to remotely enumerate all the callbacks present, and also, because we've got that slot data, any parameters provided to them. So for the sake of completeness, look, we've achieved those goals. We've got our fibers, we've got our dormant fibers, we've got our fiber local storage, all the indexes, and then we've got the correct thread IDs, and we can match them up all together. So now we've built this raw telemetry, we can apply a set of enrichments, much like we would do with suspicious threads. So for fiber data and fiber local storage, we'd look at the memory page protections, the location and size of that data, and then also generate some entropy scores to see if it's encrypted or compressed. And then for the fiber callbacks, we can look to resolve the module of which the callbacks are located in, and then also the parameter data provided to them, and then providing that we have got contact with the Microsoft symbol server, we can then resolve the function name. And then we can start generating rules, such as some of the things I put down was fiber data executing from unbacked memory, or encoded, encrypted fiber data, callbacks to strange locations, or callbacks to APIs known to be used by malware, or even some like anomaly-based rules. So the absence of certain fields that we know should be there, threads only using one fiber, or the absence of standard callback functions. So I combined all this research together into a tool that I built called Weetabix. It's actually an English breakfast cereal full of fiber, hence the name. And what it does all that remote enumeration for you and enriches it, pops it out into a nice little JSON, which you can ingest into, I don't know, Splunk or Elastic or whatever you're using. So why build this capability? Well, we're starting to see C2 frameworks adopt the use of fibers to evade traditional detections and also to facilitate other offensive techniques. So for instance, Cobalt Strike, everybody here is probably aware of Cobalt Strike, the de facto commercial C2 framework that a lot of red teams use. Anyway, last year they implemented thread stack spoofing in their artifact kit. And to do this, they leveraged fibers. And thread stack spoofing is when you manipulate the stack data with a fake call stack, and then that is used to evade traditional signatures. But this unorthodox way of using fibers actually looks markedly different in memory. So I ran Weetabix against a victim machine with an executed Cobalt Strike beacon, and with the thread stack spoofing turned on, and it actually gave me some pretty interesting results. So it shows threads, a thread only using a single fiber. Why use a single fiber when you can achieve the same thing with a thread? There's no need to get a fiber involved. And then 1, fiber data of this fiber was pointing to some unbacked region of memory. 2, there was no fiber local storage slots. And 3, there's no callbacks, no like standard callback functions that you might expect. So now we've got this telemetry. It's really easy to write rules for it. It's quite trivial. So here's another example where I tested it against the malicious callback technique from earlier. So Weetabix finds 2 suspicious callbacks. The first is a callback to a module in the downloads directory. That looks really sketchy. And then 2, a callback to unbacked read-write executable page permissions. Both very trivial to write rules for. So can we go further? Yes, we can. So the great thing about fibers is that they're relatively uncommon, which we don't bring back an awful lot of telemetry, which is good because it means that we can be really aggressive with the rules that we write and not have to worry about the implications of too much processing. And we can also tack on other things like post-processing capabilities based on the telemetry. So we have, from our fiber object, the stack information, so we can rebuild those call stacks and give us more metadata based on those detections. And because there's actually less data, it also means that it's harder to establish the norm. So I guess if anyone's actually using fibers out there legitimately, please come and talk to me, because I'd like to establish those edge cases. So key takeaways. One, attackers are sometimes going to find and leverage new and obscure ways to circumvent traditional telemetry sources. And this increases their likelihood that they remain undetected by blue teams. Two, if there's no telemetry, then there's no data, there's no evidence, and there's no detections to be had. So investing in endpoint research is vital for EDRs to remain relevant and effective. And three, providing a problem has been understood to sufficient depth, we can produce our own novel telemetry rather than piggybacking on existing sources. And this can be incredibly valuable because it only contains the information and the events that we care about, which actually makes writing detections much simpler for threat hunters. And it also puts less pressure on rules engines, back-end teams, and ultimately hosting costs. So some of the resources I found helpful along the way, Jeff Chappell's documentation of some of the Windows structures. ReactOS actually had an older implementation, pre-1903 build to fibers, which was somewhat helpful, somewhat confusing, especially to start with. And then also an ex-colleague and general good guy, Will Burgess. He was the one that kind of pushed me into look into fibers in the first place by saying, Dan, what exactly are fibers? How do they work? So yeah, thanks to Will. And yeah, thank you very much. Thanks for coming out and listening to my talk. Appreciate it.